Matching in a journal graphs, Edmonds Blossom Algorithm. Recap of previous lecture. In previous lecture we have discussed factors, perfect matching in a journal graph, Tutt's one factor theorem and F factor of graphs. Content of this lecture, we will discuss the matchings in a journal graphs, that is given by the algorithm which is known as Edmonds Blossom Algorithm. Edmonds Blossom Algorithm, if we see the details of why a separate algorithm is now required, but we have already seen the matching in a bipartite graph using augmenting path algorithm for bipartite graphs. Why it can't be used here for matching in a journal graphs, all this discussion we will see now. Now we have seen earlier that Birch theorem stated that matching M in G has a maximum size if and only if it has G has no M augmenting path. So the augmenting path algorithm called APA what it does is it finds the maximum matching using successive finding of augmenting path. This particular augmentation is carried out by the iterations of n by 2 different times, and therefore all the augmenting paths are identified and the matching cardinality or the matching size is increased every time. Now after n by 2 iterations, it is proved that it cannot be extended. Why? Because it will not find any augmenting path. Hence, using Birch theorem, the algorithm terminates with a maximum matching in a bipartite graph. Now Edmonds in 1965 presented the first algorithm, which basically is generalized algorithm for journal graphs, not only confined with the bipartite graph, but it is a generalized algorithm, and his paper was called as Path, Trees and Flowers. In bipartite graphs, we can search quickly for augmenting path because we explore from each vertex at most once. An M alternating path from U can reach vertex X in the same partite sets as U only along the saturated edge. Hence, only once we can search and explore X. Take this example. If this is the bipartite graph, that means two partite set X and Y. Let us assume that this particular vertex is unsaturated. So you can reach to any vertex on the other partite set and then take a matched edge and reach on the same side, and then take another unmatched edge and reach on other side, let us say it is Y. So when it reaches here, it takes the matched edge, to come back to the same partite set. So there is only one possibility to reach to the other side of the partite set, because matching tells you that a particular edge is incident on only one vertex. It cannot be incident on two vertices. So if it is taking up the matching edge to reach to the same partite set, then it has only one choice, because it uses the matching edge. Hence, only one choice will be there, and we can explore x in this particular manner. So that means in the bipartite graph, searching augmenting path is quite easy and fast also. But if a graph is a general graph, that means it contains an odd cycle, then reaching on the other side may have more than one options to explore. Hence, the exploration is not to that particular space in which bipartite graphs, that is the graphs which are not having the odd cycles, can function easily and efficiently can done. So this particular property that it has to explore once exactly one search, this particular property will fail in a graphs with the odd cycle. That we will see why. Because m alternating path from an unsaturated vertex may reach x both along saturated and along unsaturated edges. Take this particular example. This is an odd cycle. If this is unsaturated vertex u, when it comes over here, these are all unsaturated vertices. So there are two different openings of unsaturated vertex where to go if it is an odd cycle. Which way to go, or both ways are to be explored at the same time. So this particular property is failed here in the general graphs, the graphs especially which is having odd cycle. Hence, Edmonds Blossom has given a new algorithm to do the matching in a general graphs, that is the graphs which is having the odd cycle also, how the augmenting path can be efficiently found out. That is given here in this algorithm. So same example, let us illustrate it again regarding the problem in identifying the augmenting path when the graph is having an odd cycle. This is odd cycle. So in the graph below, m is indicated, that is the match as is indicated with the red color, and the search for the shortest m augmenting path from u when it reaches x via the unsaturated ax, then we may miss the other path which is basically a longer one, but it is reaching to x via a saturated edge. So in this case, if we choose to go directly by unsaturated vertex reaching x by unsaturated vertex, then we will be missing up this augmenting path, that is u, v, a, b, c, d, x and then y. Both are unsaturated vertices. So this is an augmenting path which will be missed out if we only follow this particular path, which is not a set. So let us see the definitions. Let m be the matching in a graph G and let u be unsaturated vertex. So a flower is the union of two alternating paths from u that reach a vertex x on the steps of opposite parity. Take this particular example. You start from unsaturated vertex, you reach x with a different parity. So this becomes a flower. So in this particular flower, this portion is called a stem, this is called a blossom, is an odd cycle, and total thing is called a flower. The terminology is drawn from the horticulture. Why? Because trees were also used in the computer science and in the graph theory also. Let me again read it out. A flower is the union of two alternating paths from U that reach a vertex x that I have told. Let us say this is vertex x, you reach via this path and you reach via this path from U, and this is the union of two alternating paths is called a flower. Reaching x. On the step of opposite parity, the stem of a flower is the maximal common initial path. So, this in both the augmenting path this portion is common, and a blossom of a flower is the odd cycle obtained by deleting the stem. If the stem is deleted, so this becomes an odd cycle and this is called a blossom. So, we have stated all these things again for your understanding, that if this is the graph G, this portion is called a stem, this portion is called a blossom, and this entire thing is now called a flower, which is highlighted. Let us see the Edmonds algorithm. We will then take an example to understand the working principle of Edmonds algorithm, and then again we will come back to the same algorithm for a better explanation. Input to this particular algorithm is a graph G, also there is a matching and unsaturated vertex U is given as an input. Idea of this algorithm is to explore M alternating path from U, recording each vertex, the vertex from which it was reached, and contracting the blossoms on the way when found. Maintaining sets S and T are analogous to those we have seen in the algorithm earlier, with S consisting of U's and the vertices reached along the saturated edge. Reaching at unsaturated vertex will identify the augmenting path. Let us initialize S with the unsaturated vertex and T is basically empty. Let us see the iterations of Edmonds algorithm. If S has no unmarked vertex, then you stop. There is no M augmenting path from U. Otherwise, it has unmarked vertex V. To explore from V, successively consider each neighbor of V, let us call it as a Y, and Y is not marked, that is not in T. Now, if Y is saturated by M, then trace back from Y to report an M augmenting path Uy. So, if you start from U, reach to another vertex Y which is also unsaturated, so immediately you will get the augmenting path. Now, if Y belongs to S, then a blossom has been found, because you have already visited that node and is there in the S. That means you have reached to a point which is already being visited and is available in S. Then a blossom has been found. Suspend the exploration of V and contract the blossom. So, blossom is contracted with one vertex replacing its vertices in S and T by a single vertex in S. Continue search from this particular vertex in the smaller graphs, otherwise Y is matched to sum w by m, include y in T and include w in S. After exploring all such neighbors of V, mark V and iterate. Let us see all these steps in a working example and then come back again. We will explain you again. In this example, let M be the matched edges which are shown in the red color in the graph on the left side. This is the graph, and the edges which are shown in the red color, they are in M. Now we search from an unsaturated vertex U for an unaugmenting path. We first explore the unsaturated edge incident to U. There are two such edges. So reaching A and B using this particular edge, you can reach A and B. Since A and B are saturated, because these edges in M, they are touching up. So we immediately extend the path along AC and BD, directly go up to this point. That is not a problem. Now S will contain U, C and D. That means you have reached up to this point. From C and D you have to go ahead, and U means you starting from unsaturated vertex. So other vertices from where you are reaching C, that has to be maintained somewhere else. Now then, if we next explore from C, then we find its neighbor E, this neighbor E and F along the unsaturated edges. Since EF is an M, so we discover the blossom with the vertex at CEF. CEF. Why? Because you explore E, you explore F, and from F to E and E to F, if you basically see which is present in S, then a blossom is discovered. So this is a blossom. So blossom with the vertex at CEF has been discovered because from two different parities we are basically touching either F or E. Now we contract the blossom. Contract means this entire thing is basically collapsed into one vertex. This is called contract. The blossom to obtain a new vertex, and that is called C, and now you have to change this S, so that S will now contain U, capital C and D. Because this will be C, so this edge will connect to D, this edge will connect to G. So this will yield the graph on the right side. This particular graph we have already obtained. Now suppose we now explore from the vertex C, which is already present in S. Unsaturated edges, this and this, take us to G and to D simultaneously. We can reach here up to here using unsaturated edges. Since G is saturated by an edge GH, we place H in S, so H is placed in S, and also D, because D we can reach. So now S will contain UC DH. Since D is already there, because we have visited D from the other side. We have found another blossom. When you reach D by this way, you have already visited earlier. Then reaching D by different parity, you will basically now identify another blossom. So this blossom also has to be collapsed into one. So the paths reaching D are U, B, D and U, A, C, D. So there that will be collapsed into a blossom, and we call it as capital U. So we contract the blossom, obtain a new vertex U, and the graph on the right, this particular with S is equal to U and H. So H you will reach from the other direction, and U when you reach via D. So we next explore from H, finding nothing new. Why? Because this is saturated. So this is not an augmenting path. Nothing is being identified through H. Finally, we explore from U, reaching an unsaturated vertex. So it will identify a path like this. So starting from unsaturated vertex, you reach to unsaturated vertex. Now we have to trace back our path. So from X, we are coming from U. Now we have to go and see within it, and within U, if you see, you have reached from B, D, F, A. So having recorded the edge on which we reached each edge, we can extract the M augmenting path Ux. We reached X from U, so we reach X from U, so we expand U. So when you expand U, so we expand the blossom back into UA, then BD and C. C was again, and find that X is reached from U along Bx. The path in the blossom U that reaches B on a saturated edge ends with C, CDB. Since C is a blossom in the original graph, so we expand C back to CFE. E is not used here, so we are not showing it. Note that D is reached from C, from that blossom C, by the unsaturated edge ED. So the path from the base of C that reaches E along the saturated edge is CFE. Finally, C was reached from A and from U. So we obtain the full augmenting path is like this. So we have started from U, we have gone to A, then we have gone to C, then we have gone to F, then we have gone to E, then we have gone to E, then we have gone to B, then we have gone to X. So this is augmenting path is being identified. Remarks. So Edmonds' original algorithm runs in of the order n raised to power 4. The implementation in Ahuja, Mangtani, Orlin algorithm runs in the order n cube, that is faster way of implementing the same approach. This requires appropriate data structure to represent the blossoms and to process the contraction, and careful analysis of the number of contractions that can be performed. The time is spent exploring edges and the time is spent contracting and expanding blossoms are reduced in these algorithms. So the first algorithm, solving the maximum matching problem in less than cubic time, was of the order n raised power 5 by 2, that is 2.5 in even Carew in 1975, the best algorithm. Now known runs in the order n root n m. for a graph with n vertices and m edges. The algorithm is rather complicated and appears in Mikali and Vazirani in 1980, and complete proof in Vazirani is given in 1994. Conclusion: in this lecture we have discussed Edmonds Blossom algorithm and also discussed the concept of flower, stem and blossom. In upcoming lectures we will discuss the connectivity and paths. Thank you.